Hello, I'm Neil, and with me are Sanjar, Emily, and Patrick, and today we'll be doing a brief overview of our semester-long security analysis of the open source project Mosquitto. If you'd like to access this slide deck or any of the reports or diagrams we reference, all of it is available at the listed GitHub repo below. The expectation of this presentation was to pretend our manager asked us to do a security analysis of Mosquitto and to present our findings. The presentation will include a brief description of Mosquitto, an overview of the security activities we engaged in. We'll report the results from running two static analysis tools against the code base, as well as our process and findings from a manual code review. Finally, we'll highlight our communications to the Mosquitto maintainers, as well as provide helpful notes if you're interested in checking Mosquitto out. So what is Mosquitto? Mosquitto is part of the Eclipse Foundation, and in a nutshell, it's an open source message broker that implements the MQTT protocol. It's easiest to explain what that means with an example below. When we say broker, for all intents and purposes, you can think of a broker as a server. Let's say that there's a blog that multiple people subscribe to, so they receive updates to the blog on their machine as soon as updates are published. In MQTT terms, subscribers subscribe to topics, so below, Brenda and Charlie both subscribe to the Fantastic Four blog topic, and their computer continuously pings the broker to see if any new material has been published to that topic. Adam publishes an update to the Fantastic Four blog topic. This message gets sent to the broker, and the broker then distributes that blog message out to everyone that subscribed to the Fantastic Four blog topic. Eclipse has a Mosquitto broker available for testing purposes at test.mosquitto.org. If you'd like to experiment on your own, first download Mosquitto on your computer, and then you can send publish-subscribe messages through that broker. Below are example commands you could type in to publish-subscribe the message "Hello World." Where Mosquitto really gets interesting is for communication between IoT devices. Think of self-driving cars sending messages to each other, or users communicating with their home automation devices. The MQTT protocol was designed with low-power computers in mind and machine-to-machine communication, so it's extremely lightweight and requires very little bandwidth. Below is an example of an IoT usage. Let's say that Professor Gandhi has home automation configured in his home. He sends a message from his phone to turn his lamp on in his living room. The home automation system's implementation might very well be using Mosquitto, or in the very least, the MQTT protocol. For repository health, the main question we wanted to answer was, is this an active project, or is it a dead, unmaintained project? What we found was that it is a very active project. The repo's been around since 2014. There's 62 contributors, but by far the main contributor is Roger Light. There's 185 currently open issues, and the maintainers are very good about staying on top of responding to issues, usually within a couple days. Transparency in regard to security is great. There's documented CVEs, and Eclipse has a blog for Mosquitto that details release notes and security patches. When looking at the blog, one will notice that it's important to be sure you're using the latest version, which as of this recording is version 1.5.4, because it patches a security vulnerability.
Hi, this is Emily. I'm going to talk about the gaps in our security requirements and give a little bit of the background story behind our project. Our project reviewed Mosquitto as a service being implemented in a package delivery and fleet management scenario, using the publish-subscribe style messaging to aid delivery trucks in the fleet to publish their location, mileage, and subscribe to update on the orders they are driving to complete. The stakeholders in this scenario are primarily the drivers, who want to stay up to date as to the location and condition of their orders they are fulfilling. They also wish to be able to notify their management headquarters when they are either complete with a delivery or if there's a problem that they need assistance with. The stakeholders are also the management team who want to notify the drivers of any state changes to their orders and or who need to monitor the activity of the individual members within the fleet. Depending on the package delivery system and its customer base, you could argue that the consumers who are about to receive the packages would also be stakeholders. The first misuse case we are going to review is Bob, the delivery admin. Bob, the delivery office admin, needs to communicate to the delivery truck driver in real time where the delivery driver's next location will be. The first task required is Bob needs to create a delivery order in the system. One of the actions that occurs when Bob creates the delivery order in the system is that it publishes the delivery order to the broker, so the broker is then able to push out the order to the driver. The misuse case in our diagram is Blaze the hacker. He wants to steal a delivery package. One way he can do this is to cancel a legitimate order and then create the same order but with a different address. Our DFD model that was associated with this misuse case is represented here. Bob, the office admin, wants to create a new order. He then pushes that request and then it is returned. A preventative measure to mitigate this would be to mitigate a dictionary attack. A common strategy is dual factor authentication. Our next misuse case that we're going to go over is Henry the Honest Delivery Driver. Henry the Honest Delivery Driver subscribes to the delivery orders that Bob the office admin pushes. In this way, Henry has the delivery information needed to make deliveries and will also be informed when deliveries are canceled. The misuse case represented in this diagram is the intent of the attacker is different than in the first scenario, but the attack is somewhat the same. In this scenario, the attacker is a disgruntled driver whose sole intent is sabotaging operations. Judas, the disgruntled delivery driver, publishes messages that say deliveries are canceled when they are not. The associated DFD with this misuse case is Henry the driver wants to subscribe to the delivery order log. The subscription request goes out and then a subscription response is returned. This attack could be prevented by adding a system procedure which prevents errors when setting up or modifying the authorization policies. The third and final use case we're going to review is Jake the broker admin. Jake the broker admin creates and publishes a scheduling order log every morning. The order log contains the list of delivery orders and schedules. Other actors such as Bob, the delivery office admin, can push or cancel orders to the order log. Henry, the honest delivery driver, subscribes to the order log, and Jake can review, complete, or cancel orders, and the order log is updated based on completed or canceled orders. The misuse case here is Laser the hacker is bored and has nothing better to do with his life, so he decides to sabotage a fleet management system. He decides to attack the order log with a denial of service attack. He overwhelms the order log with connection requests, which causes an overload and prevents the legitimate request from being fulfilled. This attack could shut down the company's delivery operations. In this case, the fleet management system has contingencies put in place to mitigate the system overload due to numberless connection requests. The threat model associated with this use case is Jake the broker admin wants to manage accounts. He sends a request to manage a new user request, and then an acknowledgement is returned. This attack can be prevented by adding a rule to the firewall settings, which would limit the number of connection requests. And to prevent extensive amount of requests from a single connection, a firewall rule must be added to set a threshold to deny large amounts of traffic coming from the same IP address. All of Mosquitto's configurations are located in the mosquitto.config file. The documentation makes clear that the majority of the security features are disabled out of the box. A couple of security-related configurations that stood out to us during the review are as follows. The first is there's no maximum published payload size in the configured file. Second, the connections for logged-in users never expires. Third, there are no maximum number of client connections specified. Fourth, the SSL and TLS is turned off. 5, the authentication by publishers and subscribers is optional. 6, no authorization rules exist for authenticated or unauthenticated users. 7, all users have full access to publish as many topics as desired. 8, all users have full access to subscribe to all topics, and the last is all users have full access to metadata related about the broker.
Hello everyone, this is Sanjar, and I'll be talking about the assurance claims that we have designed based on the use cases and misuse cases that Emily just described. And our first assurance claim is that the order log maintains integrity throughout the delivery. And this is within the context of our fleet management system is since it's using Mosquitto message broker to send data to the delivery driver, there are a few rebuttals within this claim, and we have addressed them right there. Would be if an outside or an insider attack on the delivery on the order log happens, then the integrity of the order log will be questioned. So what FMS allows, and to answer those rebuttals, we have two claims that show that FMS only allows authorized and authenticated users to alter delivery orders. This will be discussed further within the next assurance claim, but for this claim we have a rebuttal that what if there's a dictionary attack by an unauthorized user and they get access to the password of an authorized user? What do we do? So in that case, FMS, our fleet management system, requires strong passwords, and that will mitigate the dictionary attacks. And for this top level claim, the only other rebuttal would be for an insider attack with proper authorization levels, order delivery log. And we make a claim that the FMS maintains logs of users who altered the order log. So in that case, if an authorized user is gone disgruntled and they make any changes to add the order log, to alter the order log, it will be recorded within the log file and the Mosquitto config file and the logging. So the second assurance claim that we have derived for a fleet management system is that the FMS prevents denial of service attacks in the published order logs. And this is important because the order log is used by all entities of FMS. Therefore, FMS ensures the availability of the order log by preventing and mitigating all kinds of denial of service attacks. But there are a few rebuttals against our claim. So the first rebuttal would be, what if the order log receives excessive amount of subscriber requests? Answer to that, we have a couple claims. The first one is that the FMS successfully throttles the number of connection requests by strict firewall rules, and so which leads us to another rebuttal that what if only one connection is sending a large amount of requests to the order log or sending a large amount of messages to the order log. This is addressed that FMS successfully denies multiple requests from the same connection, and this is addressed in the Mosquitto config main page. If an boolean called allow duplicate messages is set to false, it limits the number of duplicate messages to only one. This option is useful when clients are subscribed to multiple subscriptions that overlap. In addition, this feature prevents denial of service attacks by denying multiple illegitimate messages coming from only one client. And for another rebuttal, that what if our claim is that the second claim was that FMS only allows pre-authenticated users to subscribe to order log, and this is addressed in the Mosquitto config main page, again under the general options sections of the web page. And there's a boolean called allow anonymous, which determines whether clients without credentials are allowed to connect, but FMS has set that boolean to false, which means that we can stop all incoming traffic from unauthenticated clients and and that will prevent a possible denial of service attack. And these files are found within the Mosquitto config file under the general options. Due to time constraints, we will not be going over any more assurance claims, but we have a couple more assurance claims addressed. Feel free to go into our GitHub repo and take a look for yourself.
So after putting together our use cases and assurance cases and generating our evidence needs, we then started to put together automated and manual reviews of the Mosquitto code. For our automated reviews, we ended up using two static analysis tools, Codassi and Flaw Finder. We had experimented with a few other tools, but we found that both of these gave us the results that fit best with our expectations and also found issues that we hadn't thought of yet. With the Codassi review, we ended up finding 543 issues total, with 228 of them being security related. I won't go super into detail on all 228 because that would take quite a while, but most of the issues of note were the CWEs that we ended up finding the most issues from were CWE 126, which is a buffer overread, CWE 20, which is improper input validation, and CWE 732, which is incorrect permission assignment for critical resource. For our flaw finder review, it was the same code that was reviewed, and we ended up finding 483 issues. All three of the issues that I mentioned earlier were brought up heavily, but some other issues of note were CWE 134, which is the use of externally controlled formatted strings, CWE 190, which is an integer overflow or wraparound, and CWE 362, which is shared resource with improper synchronization. With those results in hand, we then found our points of interest to look at within the code for our manual review. So the bulk of the CWEs that we ended up finding were actually false positives, specifically CWE 126 and 120. This was mainly due to many of the strings used in the code not being checked for they're null terminated strings. They were flagged as false positives mainly because of the size restrictions of the MQTT protocol. How memory was managed when using the publish and subscribe methods for this program were that enough memory was always reserved for every publish and every subscribe request that fit within the MQTT protocol size restriction. So therefore, every single publish request and every subscribe request was guaranteed the amount of memory that was going to be available for that request. So because of that, many of the strings that were used in the publish request weren't checked for null termination because there was no way they would go over the memory limit. This was the same case with the integer overflows because of that MQTT protocol size program, so I'll move past that. So after going through the flagged issues there, we also focused on the features that we had generated out of our requirements and assurance cases. The two new features that we ended up actually submitting issues for in the GitHub repo were to include logging of admin functions, which included creating and removing new users, in the Mosquitto password utility. So the Mosquitto password utility is actually a separate program from the Mosquitto broker, and it enables admin users to be able to create users, reset passwords, and remove users through the actual tool. Now, the tool itself is only accessible when you're logged in from the host machine. You can't access it from the MQTT publishes or subscriptions. So security is very minimal on the utility, which is why both of our issues had to do primarily with the utility. So the issue that we submitted for this logging function was brought up and actually reviewed by the creator, Roger Light, and was found not to be needed, mainly because the Mosquitto password utility is simply just a utility to complete this issue. And if we implemented logging on this utility, users could still create users outside of the password utility, which wouldn't have been logged. The second issue was that there should be password requirements that are implemented when creating new users or resetting passwords. So this utility currently has no requirements on its password complexity. So I could literally set a password of 1 or a blank password.
You can't set a blank password.
Oh, you can. Oh, that's right. Yes, I stand corrected. You cannot set a blank password. That is checked. And we thought that the requirements should be set on the password complexity. The issue that we submitted also was brought down mainly because of the same issue as the logging of admin functions. Usernames and passwords can still be created outside of this utility, so by setting this sort of requirement, it could be worked around in a malicious attempt, and so our issue was flagged as not needed. And here is a listing of the communication between the Mosquitto maintainers. There's both of them for logging not enabled on password utility and strong passwords not required. And that concludes the automated and manual review. So when working through this project, a big hurdle that we had to get over was just really understanding the MQTT protocol and how it worked. So we found some really helpful articles on understanding MQTT and specifically Mosquitto, since Mosquitto is one of the biggest names in the MQTT protocol. Another problem that we ran into was actually being able to build from the specific source code itself. That took us a while to get used to, so we also listed some helpful steps on actually getting that set up, and had a great time working with this group.
And we did as well.
All right.
With you, Pat.
Oh, thanks.